Welcome to the solutions for homework set number 11 for ECE 111. Now this homework set looks at Fourier transform. Now in the previous homework sets we looked at phasors. Phasors are differential equations with sinusoidal inputs. We like sine waves. Sine waves are easy to handle. Using complex numbers and phasors, I can analyze a differential equation or transfer function with sinusoidal inputs. What happens when the input is not a sine wave? That's actually a common problem. For example, this guy right here, let's make that bigger. Here's an oscilloscope app on your cell phone. If you have certain signals like a whistle, you get this run. Hello, there you are. That's a clean sine wave. If you have other sounds like e, those are not sine waves. They're periodic, and that's actually very common. So a common problem you run into is how do you find the output of a filter when the input is not a sine wave? So to start out, we need to input a signal that's not a sine wave. So this is the MATLAB code. It's a 1 radian per second sine wave, amplitude of 4 volts, offset by 3, clipped at plus 6.5 and minus 0.5. So there's your input. What happens when I run this through a filter? Well, that's actually not an easy problem to solve. So a typical engineering solution is if you have a hard problem to solve, change the problem. But change it in a way that you keep the flavor of the old problem, but make it solvable. For example, I can use curve fitting. Using least squares curve fitting, I can approximate x with a polynomial. We've done this before. So the trick is you set up the basis function based upon what you want. In this case, my basis function is 1, t squared, t cubed, t to the fourth, t to the fifth. Do the least squares curve fit. Again, the inverse of b transpose b times b transpose times the output, in this case x. This is the weighting on the first basis element, a0, a1, a2, a3. And if I plot the two together, time versus the data, time versus the curve fit, I can see it's actually a pretty good approximation. So I can approximate the blue line, x of t, with this polynomial. I can do it, but that doesn't really help because I know what to do with sine wave inputs. This is actually a power series input. So wrong basis. Well, doing the same trick, I could choose a different basis. Choose the basis to be 1, cosine t, sine of t, cosine 2t, sine of 2t, and so on. Do the same thing as before. The coefficients are inverse of b transpose b, b transpose y, or x, and I get a curve fit. And again, once again, it matches pretty well. What's special about this curve fit is this is in terms of sine waves. This is the weighting times 1. These two are times cosine and sine of t. These two are at 2 radians per second. These two are at 3 radians per second. I've now expressed x of t in terms of sine waves. I like sine waves. I know what to do with sine waves. With sine waves, I can use phasors, or complex numbers. That's the whole point behind Fourier transforms. Take a signal which is hard to analyze, a signal that's periodic, that's not a bunch of sine waves, and turn it into something which is easy to analyze, namely sine waves. Now, least squares is one way to find those coefficients. A second way that you normally do is note that this is an orthogonal basis. What that means is I can pull off the different terms one by one. To find the DC term, just find the average of x. To find the cosine of t term, find the average of x hit with cosine of t, times 2, and you get 0. To find the sine of t term, find the average of x hit with sine of t, times 2. The reason for the 2 is the average of sine squared is a half, so that clears out the half. This is an orthogonal basis. It's not orthonormal. If it was orthonormal, the norm would be 1, so I'd multiply by 1. It's not a big deal if it's not. I just multiply by 2. So what you do when you do this is I pull off the exact same answer we had before. These are the Fourier coefficients. Solved a different way. This is actually much easier. But either way it works. The thing to take out of that is Fourier transform is just really curve fitting. There's no difference between curve fitting and Fourier transform, except I'm using a very special basis. The basis that I'm using is made up of sine and cosine terms because I know what to do with sines and cosines. So for example, suppose I have that periodic input hit with this filter. Find the output. Well, this is where we use the property of linearity and superposition. Linearity says that f of a plus b plus c is f of a plus f of b plus f of c. That's linear. What we're going to do is, this is x of t. It contains a DC term, 1 radian, 2 radian, 3 radian per second terms. Treat that as 4 separate problems. Find the output when the input is a DC term. Find the output at 1 radian per second. Find the output at 2 and 3. So, starting at DC, if the input is DC, the first term, I can find it. This is the gain everywhere. All I care about is what's the gain at DC. At s equals 0 times the input at DC. Plug in s equals 0, I get 2 over 1.5 times 3.27, 4.3. So that's the DC term of y. In MATLAB, I can do that by just saying s equals 0. That's the input, and here's the output. The gain at this very special value of s times the input at that frequency. Now let's go to the second term. At 1 radian per second, here's the input. In Phasor form, this is 0 minus j 3.3. You can remember 0, or the real part is cosine, minus j is sine. The frequency is 1 radian per second, so s is j1. Here's the gain everywhere. All I care about is what's the gain at 1 radian per second times the input 1 radian per second. Multiply those together, you get a complex number. Real part means cosine, minus j means sine. Or in MATLAB, here's the frequency, here's the input. This is what we found before using Fourier transform, cosine and sine term. Find the gain at that frequency times the input at that frequency, and you get a complex number. Real part is cosine, minus j is sine. Repeat at 2 radians per second. Here's the input at 2 radians per second. In Phasor form, it's minus 0.3067. Here's the gain everywhere. Find the gain at j2, multiply, get a complex number. Real part's cosine, minus j is sine. And the corresponding MATLAB code, again exactly the same as before, just change the frequency, change the input. I get the output at 2 radians per second. And again at 3 radians per second, here's the input, here's the frequency, there's the gain at that frequency, times the input at that frequency gives the output, cosine and sine. So when it's all said and done, add them all together, add up all 4 inputs, I get x of t, add up all 4 outputs, I get y of t. So here's y of t, and if I plot it, here's the input x, here's y. So what I've done is actually really significant. I just found the output of a filter, meaning the output of a differential equation, with an input that's not a sine wave. The way I did that is I transformed x into a bunch of sine waves. That's the Fourier transform. Then at each frequency, find the output. Now one caveat. With Fourier series, you might think you have to go out to infinity. In theory, yes you do. In practice, no you don't. And you see that here. The output primarily just contains 2 terms. If I just included these 2 terms, the DC and the first harmonic, that'd be a pretty good approximation. Each of the other terms gets smaller and smaller for 2 reasons. Most of the energy is at low frequencies. My filter attenuates high frequencies. Put the 2 together, the high frequency terms disappear. So if I ignore the high frequency terms, I'm not that far off. Oftentimes we just use the 2 terms, the DC and the first harmonic. Occasionally I might use a couple terms, like the DC, first, second, and third harmonic. Call that good enough. With that approach, you don't have to go out to infinity. I can get a very good approximation of y just using a couple terms. So that is homework set number 11 in ECE 111. The thing to take out of this is with MATLAB, you can solve problems pretty easily. When you get to signals and systems, you'll cover Fourier transforms, and that really confuses people. People really struggle with Fourier transforms. Think of it as just a curve fit. You can curve fit anything. I can curve fit x of t with a power series. I can curve fit x of t with a bunch of sine waves. Fourier transform just says use the sine waves as the basis because I like sine waves. With sine waves, I know what to do with sine waves. With sine waves, I can use superposition. With sine waves, I can treat this as 4 separate problems, analyze each one separately. That's the whole point of Fourier transforms. So that's homework set number 11 for ECE 111.